Again, there are two laws. There's a current law and a voltage law. So let's look at the voltage law first. So the voltage law states that if you see a loop, the sum of voltages in the loop adds up to 0. So sum of voltages in a loop adds to 0. In other words, it will be summation I equals 1 to n, Vi equals 0, where Vi are the individual voltages. So to give you an example, if you have 4 voltage sources, and let's just put some signs on them just to show the polarity. So V1, V2, V3, V4. Okay, so for example, the positive of V2 is connected to the positive of V3 and so on. So if we want to use KVL or Kirchhoffs voltage law, then you'd say summation of Vi, where I goes from 1. In this case, there are 4 voltage sources, should be equal to 0. So we have V1 is connected, so V1 has a positive, so, and that's connected to the negative of V2. So let's just randomly assume that we're going to stick with the positive sign for V1. Now V2 is connected in the same way as to V1, right? So negative goes to positive, so we assign a positive sign to it. V3 is slightly different. The positive of V3 is connected to the positive of V2, so that's going to effectively be negative because positive is connected to positive, not to negative. And then V4, we can see that it's connected the same way, the usual way to V1, so we'll put a positive sign. Okay, so this is the summation, and that should be the, so in other words, you need to be careful about how the voltage sources are connected individually. You can't just randomly sum them. There's a Kirchhoffs current rule, which we'll do next. So B current law. Okay, which states that, so for voltages, it's always a loop. For current law, it's always a node. Node is where multiple wires join, connect to each other. So sum of currents at a node add to 0. Okay, so summation I equals 1 to n, I of I equals 0. So let's see how to do this. So if you have a node and wires sticking out, say this is I1, this is this direction, I2 in this direction, let's say I3. Let's call this node as new node A. So at node A, we can write, so everything going in should add up to 0, and we need to be careful about the signs. So just choose one convention you want. Everything going in, let's say, is positive. So positive I1, since it's going to A, positive I2, since it's going towards A, and then I3 comes out, so we'll put a negative sign. Okay, so this is how you will write the current. It's basically saying that current cannot just disappear. Whatever goes in comes out, and that's what it is. So that's those are the two rules we'll need in order to analyze circuits. Okay, so let's look at some of the most simpler circuit, a series circuit and a parallel circuit. And we'll use the KVL and KCL, which I just talked about, in order to analyze these. Okay, so here are two resistors connected to a voltage source. Let's call that V. And our goal is to, say, compute the current in the circuit. Yes, so let's just redraw that. Okay. Okay, start assuming some direction for the current. It's usually, I mean, you can assume either direction, it's fine. Let's just assume it this way, I. And here we have the choice. We can use either KVL or KCL. One way of thinking of this, and maybe this is, it's good to think in terms of voltages so that you can then look at other things. Because there's a current which flows through each resistor, there's going to be a voltage drop across the resistor. So let's just start assuming that there is some voltage drop across R1 and some voltage drop across R2. Okay. And so now I intentionally put this as positive because my assumption is the current always flows from the positive to the negative. So if it's put this way, then it will follow the convention. So now what we can do is we can use KVL because it's a closed loop, and write down summation V equals 0. So here we have V since this positive is connected to that positive, we need to put a negative sign, and the same for VR2. Right, so I'm just following the same convention I followed earlier. Now, there's a constitutive equation between VR and I. We know that VR1 is I times R1, and VR2 is I times R2 equals 0. So we can then simplify and write a formula for I. It's V equals R1 plus R2. Okay, and if you would like to think of, there is a effective voltage, that is, you can reduce this to a simple circuit involving one resistor and one voltage source, then this would be R effective. And that R effective, you can see, is basically R1 plus R2. So it turns out that if you have a circuit in series like this one, two resistors connected in series, then the net resistance is the sum of the individual resistances. So you need to sort of remember that, because when you will analyze more complex circuits, you can break down to series and parallel circuits, which you're going to do next. So R effective is R1 plus R2. Okay, so that's one part. The other part, which I think is very useful, especially when you're doing any debugging any circuit, is to understand what is the voltage drop across individual elements. So here we have two elements as VR1 across across R1, VR2 across R2. We can compute that quite easily now that we have the current. So VR1 by the constitutive relation is I times R1, but we solved for I, that's V divided by R1 plus R2 times R1. Okay, and I can rewrite this as R1 divided by R1 plus R2 times P. So what you see is that the voltage across R1 is the fraction of the resistance, right? So R1 is the voltage, is the R is the resistor across which we're computing the voltage, and that divided by the sum of the resistance is the voltage. So this circuit is known as the voltage divider because you can easily use this formula to compute the voltage. You don't have to go through the whole process of computing I. So it's good to remember these things because when you're debugging circuits, you can just remember this. So this is known as voltage divider. Essentially, the circuit divides the voltage across the two resistors. Okay, now you can try these things out. You can try to analyze a circuit involving a capacitor and inductor. C1, C2, and inductor L1, L2, and try to compute effective capacitance and inductance. Okay, I'll write it down here, but you can do the same formula. You can use the KVL, KCL to do that. So the effective capacitance for series is actually C1, C2 divided by C1 plus C2. And the effective inductance is L1 plus L2. So inductors are more or less like resistors when it comes to the net inductance, and capacitors are slightly different. Capacitors actually look very similar to what you'll do with a parallel circuit. Let's look at a parallel circuit next. Yes, so a parallel circuit has the two resistors in parallel. Here is this is in parallel because of the way it's drawn, like they're in parallel. But the way to think about this is that they actually have the same voltage applied to them. So R1 has voltage V, R2 is also the same voltage V. If you compare this against the first circuit, the series circuit, you'll see that the voltages are not the same, right? So the voltage across these two ends is not V because there is R2. Okay, so we have this circuit, and the question is compute the current in this circuit. Compute the current, and let's also do the effective resistance. Okay, so we do the same thing. I'll just redraw this and then assume some current and then evaluate what the current is. Okay, so what I'm going to do is I'm just going to assume that this is some current I flows, and I'm assuming that this way, but there's no hard and fast, so you can assume it to be the other direction too. You'll get the same answer. You'll get negative of whatever I get here. So here at this node, the current I splits into two. And now I can again make a this is hung. Okay, so I can assume whichever direction I want, it's either direction is fine. Just to be convenient, I just assume it to be in this direction for R2, and then in this direction for I1. So this I2 will flow here, it'll come here, and this I1 will flow this way, and it'll come out here. And there's going to be I because that's the one, and you'll see that it's the sum of the two currents, right, when you use KCL. So now let's analyze this circuit. So we use KVL, KCL. In this case, for KVL, okay, which says the summation of voltage is 0, we have two loops here. This is one loop. Sorry, there are three loops. Not bad. There's a second loop, and then there's this. I should put it this way. This is one loop. This is the second loop, and then there's this third loop. The whole thing. And it's perfectly fine if you use KVL on any of these. In fact, you shouldn't use it for all three loops. You only need to use it for two loops in order to solve for the things you're interested in, I1, and I2, provided you use the KCL also. So let's say that we use KVL on the inner loop on the left side. So this one. So we have V equals I1 times R1. Okay. If you use KVL on the bigger loop, which is the outer loop, okay, and just doing that because it's slightly more convenient, you can write I2 R2. If you did want to use it on this loop, then you would have something like this. But I should write V1 minus R equals 0. If you use it on the right one, it would be I1 R1 minus I2 R2 equals 0. Right? And you can see that if you subtract this equation from this equation, you should get the third equation. So it's really no point writing three equations, just two equations. They're just redundant. Okay, this is 1, 2, this is 3. This comes from 1, this comes from 2, this comes from 3. Okay, now let's try to count the unknowns and knowns. In this case, we have 1, 2, and 3 unknowns. So 3 unknowns, we need 3 equations to solve for the unknowns. Now the issue is that you can't use these three equations as 3 equations because they are dependent. In other words, you can derive equation 3 from equation 1 and 2, so they're not really independent. So don't use these 3 equations and solve for I1 and I2. You will not be able to do that. So we have to generate the third equation because there are 3 unknowns. The third equation comes from KCL. So applying KCL. And for that, what I'll do is I'll choose this node, and you can see that on this node, I comes in and I2 and I1 go out. And so I minus I1 minus I2 is 0. So I equals I1 plus I2. So in summary, these are my equations. V, or let me write it as I1 R1 equals V, I2 R2 equals V, I1 plus I2 minus I equals 0. And I just wrote it down so that the unknowns on the left side and the knowns on the right side. And then you can solve this in multiple ways, including writing this as a linear equation. But here you can solve for I1 using the first equation. You can use the second equation to solve for I2. And you can use the third equation with what I found for I1 and I2 to compute I. So I is going to be V divided by R1. Right? So from this, we can now try to compute the effective voltage. It's going to, effective resistance. It's going to be I equals, I'm taking this equation and writing it as R1, R2. Okay, so what we do is we write this as V divided by R, V divided by I, which is the R effective, is R1, R2. R1 plus R2. So the effective resistance is what I have here, which is R1 times R2 divided by R1 plus R2. Something which you should probably remember because it comes so very often when you work with hardware. Okay, so now that we have the effective resistance, let's compute the individual currents in the two branches. So I1, you can see is V divided by R1, and I2 is V divided by R2. So let's use that. Okay, I'm going to substitute V from this expression. V is R1, R2 divided by R1 plus R2 times I. So right, so that's the substitution for V divided by 1 divided by R1, which is this. And so simplifying this gives me R2 divided by R1 plus R2 times I. And then you can do the same thing for I2. It'll come out to be R1 plus R2 times I. Okay, so remember we were analyzing this circuit. Okay, so I1 and I2 were the currents here. Okay, so what's happening here is you can see that the total current, the net current, is getting divided as a ratio R2 divided by R1 plus R2. So this circuit is called current divider circuit because what it does essentially is divides the currents into two parts depending on the values you choose for R1 and R2. So this is the parallel the current divider circuit. Okay, and then for homework, you can try to do this with capacitors and inductance. So what if you have two capacitors in parallel or two inductors in parallel? So C effective in this case is going to be C1 plus C2. And L effective is going to be L1 times L2 divided by L1 plus L2. Okay, so you can try that. It's just applying KVL, KCL for that circuit. Okay, now let's look at a real example where you have a circuit given and then you're told to evaluate current. So this is, as I said, going to be useful later on when you're trying to build complicated circuits. Okay, so here is an example which will put together whatever we did so far. Ten omega R2 is 20 omega. R3 is 5 mega. Node A. This voltage source is 14 volts. Okay, so the questions are: one, compute equivalent resistance That's the effective resistance. Compute the currents through R1, R2, R3. Compute voltage at okay, so you could potentially start drawing current and then evaluating effective resistance, just like I did previously, but it's much easier if you remember or have access to the formulas I derived earlier. We need two formulas. One is for resistance in series and resistance in parallel. So we can just break it down successively as series or parallel and then compute the effective resistance, like I'm going to do now. So part one. Okay. So what you want to do is, when you're doing this, you want to avoid starting with loops with voltages because it's just hard to, because you just don't want any voltages to affect the computational resistance. You just start with things where there are no voltages. So things on the right side are nice because there's no voltages. And this trick usually works when you don't have voltages. So if you had a voltage over there on the right side, then it just becomes hard to do what I'm going to do. Okay, so let's start from the right and work our way to the left. So we see that R2 and R3 are in parallel, right? So we can write the net resistance. So resistors in parallel can be written as R2. So the effective resistance can be written as R2 times R3 plus divided by R2 plus R3. And what that effectively does is it reduces the circuit to something like this. Which is R23. Okay. And now we have just two resistors, R1, R23, and we can see that those two are in series. So what we can do is we can now find the net resistance is going to be R1 plus R23. I'm just using the series law, the series formula I derived earlier, but now that 2, 3 is combined into one, like I've shown there. So now we can draw this as a single resistor, and that's why I call it R effective. And so that's the formula. So if you want to expand it out, it comes out to be R1 plus R2, R3 divided by R2 plus R3. If you plug in the values for R's, you get 14 ohms. Okay, so that's part one. Now we need to compute the currents through R1, R2, and R3. Okay, now what we can do is, from this circuit, we can immediately compute the current passing through R1 and R2 and R3, right? We know that there's a single current going through them. There's no loops, there's no nodes, right? So we can use this circuit, the one which I highlighted, to compute the current through R1. Okay, so the current through R1, which I can draw here, is V divided by R effective. So V is 14, R effective is 14, so I1 is 1 amps. Okay, so we got I1. Now let's try to use that to compute the currents through 2 and R. So don't quite need let me just draw the whole thing, but we don't really need anything about the voltage source now. So I'm back to this original circuit. I've already computed I1. R2, R3. And now let's just say that it splits itself into I2 and I3. Okay, so note, we know I1. We already computed that. We need to compute I2 and I3. Now, one option is you could do the same analysis I did earlier, do KCL, KVL, but we know the current divider. This is a current divider circuit, right? The one involving R2 and R3. So we can just use that formula. So we know that the formula for I2 is it's a fraction of I1. Right? I1 is the current which is going through both the branches. It's going to be the sum of the two resistors. And for the fraction, we need to multiply with R2. R3. Right, so if we go back to this formula of the parallels, okay, so I1, here's I1, was R2 divided by R1 plus R2. So it's always the resistance of the neighboring branch. That's where we go back here, we see that I2 is R. I did a mistake here. I should have, the notation isn't correct. This should be I2, I3, it should be I2. Okay, so it's that of the neighboring branch. So I2 is going to be that the resistance of the neighboring branch divided by the sum of resistances. And similarly, I3 is going to be R2 divided by R2 plus R3 times I1. Okay, so the resistance are given. I1 is already been computed. It's 1 amps. And so I can compute I2 and I3. I2 comes out to be 0.2. I3 comes out to be 0.8. Okay, and then the last question is to compute the voltage at node A. Node A was this one. Okay, so the voltage across node A is nothing but, it's also the voltage across R3. Remember, this is connected to the ground, right? This is the negative or the ground, and this is the positive. So it's also the voltage across R3. But the voltage across R3 is the current through 3 times resistance 3. So I3 is 0.8, and R3 is 5. So that's 4 volts. So VA is 4 volts. Okay, so why is this important? What happens is when you are, and that happens very often when you wire something. When you wire something, you see that, for example, a motor is not functioning, is not spinning fast enough. Then next thing you do is you compute the voltage drop across the motor. You see that the voltage drop is, not voltage drop, but the voltage which is supplied to the motor is less than what you would expect. So then between that and the power supply is probably a resistor which is drawing the current. And that's your starting step to debug the circuit. If you know that there is some parasitic resistance which is causing a voltage drop, then you can use a simple multimeter, which has a voltmeter in it, to debug the problem. So using that function of the voltmeter functions is kind of central to debugging a circuit. And that's why you want to know how to use these rules and analyze the circuit. Voltage drop is one of the most powerful way of debugging a complicated circuit. Okay, we have time for one more question and then we'll stop. Okay, so here's another example. R2, R3, R4, R5. Node A. We give you the values for these. The voltage is 10 volts. R1 is 1 kilo ohms. R2 is 2 kilo ohms. R3 is 3 kilo ohms. R4 is 4 kilo ohms. R5 is just 1 kilo. Okay, for circuit like this, compute equivalent resistance. Number 2, voltage at node A. Three, current through resistor R5. Okay, just copy that before we start. Okay, when I see something like this, it just looks too complicated, right? Because there are so many grounds. But it turns out that this has been sort of manipulated or drawn in such a way that sort of, when you stare at it, it looks so confusing. But I'll show you that it's actually much simpler than what it looks. And the fact we're going to exploit to get this, to simplify this, is the fact that those things shown there are all grounds, and we can just connect all of them to the same voltage source, right, to the negative of the voltage source. So this is what we'll do. We'll draw the voltage source, and everything will come out from, this is the ground, right? Everything will come from there. So we'll connect this with each of these grounds, and you'll see that the circuit will become much simpler and easy to analyze. So let's start from, we can start, let's say, R1. So note that R1 is connected to the voltage source, and it is, it has the same, so this thing and this can be joined because they're ground. So what we do is draw R1. And then for a second, if you hide everything on the right side, then it does look like what we wanted, right? If everything was there, then that was what would be the voltage, the circuit would look like. So we're done with that. Let's move on to R2. So R2 is, we can see it's splitting here. That means that it's in parallel with R1. So R2 is like this. Let's draw node A. Okay, now we have from A, we have to go through R3 and then to the ground. So as I said, ground is this, anything connected to this wire is the ground. So let's just go. This way, and this should be R3, right? So it follows the same logic. A is connected to R3 to the ground, and they have not made any error in drawing that because it's connected to the ground as shown. So R3 is connected to A and ground, which I've shown here. Next, A is connected to R4. Okay, but R4 is connected to R5. And R5 is connected to the ground, which is this. So you see, this is the circuit, but you can just draw it in a confusing manner. It's much harder than less. So now it's, I think, tractable. We can now think of computing the effective resistance. Let's just do that. Okay, so I'm not going to draw multiple figures, but if you think it's easier for you to draw multiple figures and analyze, go from series, like analyze things in series parallel the way I did earlier, you can do it. Feel free to draw multiple diagrams, but I'm just going to just write down the formula, but go step by step. So first, we see that we have to start further away from the voltage source. So start on the right side. You see that R4 and R5 are in series. But series is R4 plus R5. Now, once R4 and R5 are combined, we see that the combination of R4 and R5 will be in parallel with R3, right? Because they share the same same two ends. They're connected to the same two ends. So R3, 4, 5 will be R3, R4, 5, R3 plus R4, 5. So I'm using the resistance in parallel to compute that. Okay, now once I have that, maybe it's easier for me to draw it so that it's easier for you to understand. So right now I'm here, R2, and this is my 3, 4, 5. Okay, so next step is to combine 3, 4, 5 with R2. We can see that those two are in series. So R2, 3, 4, 5 is R2 plus R3, 4, 5. Okay, so once they are combined, then the combination is in parallel with R1. So we have R effective is R1 plus R2, 3, 4, 5. Okay, so all you do is now compute R4, 5, compute R3, 4, 5, and just work the chain with numbers, and you get R effective. So R effective is (0.795 kilo ohms. Oh, my bad. Yeah, good catch. So R1, R3, 4, 2, 3, 4, 5 divided by R1 plus R2, 3, 4. Okay, so let's see what else we need to compute. We need to compute voltage at node A and current through resistor R5. So voltage at node A, which I think we can look here and see that the voltage in node A is going to be either if you can find the resistance, the current through R3, right? So if we can compute this current, then, well, that's not right. If you know, so we need more than that. So we probably need to compute voltage across R2, and then we need voltage across R3. And then the net voltage, which is applied across this, is going to be VR2 plus VR3. So if we can compute I2, and if you know I3, then we can, so V across node A, and there are just many ways of doing this. So one way is to compute I2 and I3. I2 R2 plus I3 R3. Okay. Another way could be, if you can find the current through R4 and R5, it will be VR2 plus VR4 plus VR5. I'm just trying to do the minimum thing. So if I can find I2, I3, then I can get it from here. So R2 is known, R3 is known, I2 and I3 are unknown. So the question is, how can I get I2 and I3? So first I need to compute I1, and this current, let's say it's I4. Okay, so I need to get I2, I3. So we know what I is. I is going to be V divided by R effective. So we can compute I. Then what we can do is, so instead of trying to solve it completely, let me just give you hints how I do it, and then let me fill the dots, and then you can refer to the notes later on. So once we have I, which I know because I know R effective, this is R1, this is R2, 3, 4, 5. So I need I2, and I2 is, I can get that from the current divided circuit. So it will be R1 divided by R1 plus R2, 3, 4, 5 times I. This will give me I2 because I is known and all this is known. Once we get that, we can then go a step further and then do the same thing for the other branch, I2, I3, I4 branch. So we can write this as okay, so this is R3, R4, R5. This is I4, I3, and I2. So if you want to compute I3, that's going to be I2, some fraction of I2, and it's going to be, again, I use the current divider rule, and I compute the fraction, which is going to be R3 plus R4, 5. R4, 5 is the combination of 4 and 5. And then that fraction is going to be R45 divided by R3 plus R45. So I2 is known from the previous step. R45 is something I computed earlier, so I think we can compute I3. And then using this formula, I can find I2 and, sorry, VA, right? And then the final step is to compute the current across resistor R5. Okay, so the current across resistor 5 is nothing but I4. So I'll complete this later on, but let me just write this down. I4. For I4, we can again think of the current divider rule. Just like I wrote the current divider rule for I3, I can write this as R some fraction of I2, because I2 is the current flowing inside. So the fraction is going to be R3 divided by R3 plus R45. And that's it. That's the answer. Okay, so the values are VA is 4.84 volts. And I4 is 0.97 milliamps. Okay. Now, this is not the only way to do this. You could do it a number of ways, including KVL case. You can always go to the basics and solve this.